let's start. Let's continue from the statement where we left in the last lecture. That was we were talking about the equilibrium of the mechanical system, and then we talk about this static equilibrium. That means all the forces are acting on the system, but overall the force, the effective force or effective torque, is zero, and the system is, the velocity of the system is zero. The velocity is effectively zero. The system is static, there is no motion. So that is this is what, if you remember, this is the slide of that. So the force is zero and torque is zero, and then the total velocity is zero, because as this book is at rest. Okay. So now we move to the dynamical equilibrium. So dynamic equilibrium, that the system is in motion. Okay, so a body is in dynamic equilibrium if it is moving with constant velocity. So that means there is no acceleration, while the net force and the net torque are still zero. So if something is in motion, then the concept of the dynamic equilibrium is there. So like if a car is moving with a constant speed in a straight line, so when a car is moving, the forces are acting, okay, but those forces are not producing the acceleration. The main thing is there should not be any acceleration. Okay, so it's moving with the, in a straight line with the constant velocity. So when the car moves, you see that when car moves on so what you have is like this is my car is moving. So when this car is moving in this direction, so the force by the tire is in this direction, and the friction is in this direction. Okay, so because the tires are moving this, like in this way, to move further, so the pressure or the force by the car on the road is in this direction, so the friction is acting in this direction. Similarly for this, so the forces are acting when the car is moving. Still the forces are acting, but the car is moving with a uniform velocity, but there is no acceleration. So this system is in dynamical equilibrium. Similarly, if you talk about the dropping of the raindrop, if you remember, you drop a stone. So if you drop a stone ki baat kare, so if you drop stone, then it will come down towards the earth freely with effective acceleration is g. But for that, what is happening, that if at some position its velocity is v1, then on another position its velocity is going to be v2, and this, then while it is coming down, its velocity is going on increasing. That is, v3 is greater than v2 is greater than v1, but the overall acceleration is always going to be g, because the difference, the increase in the velocity says that the overall acceleration is going to g, because it's falling freely. But if in terms of, in for the case of the raindrop, what is happening when the raindrop is like coming down, okay, so the g is there, and the air, if like here, if we neglect air resistance, okay, but if the air resistance is there, and this is g, because of this the air drop, this drop is coming down. So after coming down at one position, after certain travel time, there it will achieve a terminal velocity. That is a constant terminal velocity through which it will go down. Okay, so because at that time the air resistance will counter the gravitational force, and then it will achieve a constant velocity, and then it will come down towards us after certain height. It will come down with the constant terminal velocity. Okay, so that means the velocity, like when it attains the terminal velocity, and this is going to be terminal velocity, but it is such that the g is always maintained, because once it attained, then it is falling with this constant terminal velocity with this g. Okay, so in dynamic equilibrium, the system is in motion, but the acceleration is not zero. So we have equilibrium, static and dynamic, and then this virtual work. When I have a virtual displacement, okay, that is, let's define by the virtual displacement WD, delta W, because we talk about this delta Ri, the virtual displacement. So the corresponding work, that is known as the virtual work, when the forces are acting on the system. So this is what the forces of the ith particle, and delta Ri is virtual displacement, and F dot ds, we know that it's going to be the work. So this is my mathematical formulation of the virtual work. Okay, so virtual work is the imaginary infinitesimal work done by the force acting on a system during a virtual displacement. And we talk about this is virtual displacement. What is virtual displacement? Now with this, we know that what is virtual displacement, what is virtual work, what are the equilibrium thing, then we can define the principle of the virtual work. So suppose the system is an equilibrium, and what equilibrium we are talking about? A static equilibrium, that is all forces are static equilibrium, that is all forces are acting effectively are zero. So there is no velocity to the system. So the total force on each particle is zero. So like if the normal force and the reaction force are there and there is no motion of the system, this block is at rest. This is static equilibrium. So the total force on each particle vanishes. Okay, then because it's in static equilibrium, then the total virtual work, this is total virtual work done by all the forces which are effectively zero acting on the system during any possible virtual displacement consistent with the constant is going to be zero. Okay, so this is what, that if certain the forces are acting on the system, whatever the forces like applied forces, constant forces, how many types of forces are acting along the system, but if the system is in a static equilibrium, that overall the forces are zero, then and because of that force at any instant of time those forces are doing some virtual work, because you are saying that it's in a static equilibrium, but we talk about the virtual displacement. Okay, so if there is a virtual displacement because of those forces, then the work done by those forces in doing the virtual displacement is always going to be zero. Okay, this is what the principle of virtual work is there. So now so this Fi here, which is all types of forces that can act on the system, one is which we are applying, this is the applied forces, and the second contribute to the constraint force, like in pendulum. Okay, you have weight of the force and you bring this, like you bring this here, but the tension in the force is the constant force which you are not applying. So applied force plus the constant force is going to be on the system, and then because of that the virtual work done by is always going to be zero and together in a static equilibrium. So we have, if I put this into this equation, so if I have this Fi dot delta Ri and this Fi dot this delta Ri is going to be zero. So now this is my expression. Now we restrict ourselves to the system for which the virtual work of the forces of constant are zero. That means what we are doing is we're constantly restricting ourselves that this virtual work, this is the virtual work done by this constant force, because force times the displacement, virtual displacement, and that is going to be zero, constant, because of the constant is zero. This is what I am trying to say. Okay, this is what. So we now restrict ourselves to the system for which the net virtual work of the forces of constant is zero. So this is zero. For example, if you see that the bead sliding on this one, okay, where delta R. So when this will happen, when this is going to happen, when only this force is perpendicular to the delta I, because you define F dot ds, this is going to be F ds cos theta. If this is going to be zero when theta is 90 degree or F is perpendicular to ds. So that means the forces of constant are going to be perpendicular to the virtual displacement. Okay, so if I suppose this bead, the constant force on this bead when it is moving along, is n, which is the constant force, and it displays like displacement is, virtual displacement is along this direction. Okay, along this direction. Okay, so you see that this is constant for, and this is perpendicular to each other. So this delta W, the virtual work by this constant force, is zero because they are perpendicular to each other. Similarly, in this case, if like when the bead is coming down, okay, or so this is the bead is going up, so it's going from here to here. So displacement is basically you see dr is here, and then with this velocity, this is moving along this with certain velocity. So from here to this distance, from here to this distance is vt, and this is my virtual displacement. So actually this my dr is like this vt plus this vector. Okay, so but the force is, the constraint force is my n. So if I take this delta w with the n dot dr, or because we are summing over it, so it doesn't matter, we sum over all the forces over I, so it's going to be overall w. So n dot dr, because n is perpendicular to this dr, this is like this, so this n is going to perpendicular, but this is not perpendicular to this one is not going to be 0. Okay, n dot dr is not going to be 0 for vdt. This is going to be 0 for this delta r only. Similarly, in this case, we can calculate this this displacement work. Basically, the virtual work done by this constraint force is going to be 0. Fine, and let's try to see that here. We can calculate it. First possibility is, now try to understand using the Newtonian mechanics. This is my simple pendulum. Okay, so let us solve this simple pendulum problem with the help of the static equilibrium conditions, or where we are going to balance all the forces acting on the system. So first let's try to look into that, what kind of forces are acting on the system. First is like, this is my fg, which is because of m, and the direction of the is j, because you know y minus is there, because this is plus j and this is minus j, y axis. And this tension which is acting, the constraint force is tension is acting, is t sine theta, this x component, and this is x component, and this is the y component. So x component is like t sine theta, and this is t cos theta j. Okay, so it is along and then what is the total force? Total force is like two forces are acting on this. This one is minus mg, this one, because of this, and then the constraint force is my because of the tension, that is going to be minus t sine theta, and this t cos theta. With jj we couple this j with j part, and I is there. Okay, so I is there. So now this is my total force which is acting, the applied force plus the constraint force. So it is going to have two component, fx, and this is going to be fy. Okay, so this is my s component, so because of this I, t sine theta, and this is my y component, this is my fy. Now once we have fx and xy component, because we are doing Newtonian mechanics, so now these are independent. So along the s, I can have this m d2x by dt square is my fx, so that is m is there, and this d2x is x double dot, and then this fx is my t sine theta. Okay, and similarly I have m d2y upon dt square is my fy. So this is this equation. So I can solve these two equations, and this is what you get, my double dot equal to mx double dot cot theta and minus mg. Okay, this is not a big deal, you can solve it, and you can take it outside, because so now using this I have get rid of this this constraint force t, and now I have my double dot is equal to mx double dot cot theta and mg. So I have now x and y component. So x is L sine theta and y is minus L cos theta. Okay, so you see that so y is in this direction, that's why we have a minus cos theta. Okay, so from here, if I want to find the x dot, that is x dot is dx by dt, so that is delta theta of this L sine theta and delta theta by delta t. So this is going to give me L cos theta, and this is my theta dot. So this is L cos theta theta dot. Similarly for this y, I have y dot L sine theta theta dot. Okay, and then we again differentiate it, that is x double dot, this is d2x by dt square. So I have L I can take common, that is d dt of this cos theta and theta dot. So then you can have L, you can have common d dt of cos theta. If you try to find like this d dt of theta dot and keep it constant, plus d dt of cos theta and then theta dot. So what you have is L, and this is going to be theta double dot, and you have cos theta. Okay, and then cos theta is becomes minus sine theta, and you have theta double dot. So you have minus L sine theta theta dot. Okay, so this is going to be theta dot square, because when you do d dt of cos theta is basically sine theta, and then again d theta by dt. So this is going to be theta dot again, and this theta dot is going to be give you the theta dot square, because d dt of cos theta is again like this. So del cos theta by del theta and del theta by del theta. So this is or say this is going to be minus sine theta and theta dot, and this multiplied by theta dot is going to be theta dot square, and this from here L cos theta theta dot. Similarly you can find out the y double dot. So using these two equations, okay, now y double dot, you have x double dot, using these x double dot y double dot, you can do the calculation, and finally what you get is theta double dot minus g by L sine theta, and then this theta double dot is nothing but d2 theta by dt square, and you get this known relation that this is the differential equation. This is the differential equation for the simple pendulum. This is simple equation of the simple harmonic motion with omega equal to g by L, and then for sine theta for a small angle, this is for a small angle, this is for a small angle, sine theta goes to theta. So this is the differential equation of simple harmonic motion, and that we know that the differential equation of a simple pendulum is going to be a simple harmonic motion. Okay, so with the help of the Newtonian mechanics, like getting to know that what kind of forces are acting on the system, and then applying that the total force and component wise equating equal to those forces, what I'm going to get is like the differential equation. This is how we do in Newtonian mechanics. Okay, now let us apply the concept of virtual displacement, because we have seen that the work done by the virtual displacement is going to be zero. This is principle of the virtual work. So now let us apply the concept of virtual displacement and try to calculate the work done by the constant force, which is in our case is going to be the tension acting on the system. So we know that the tension is, you see that here we get rid of the tension by eliminating all this, but the tension is into play, comes into play. So when we try to solve the problem with the help of the concept of virtual displacement, so now you see that now in this case you are focusing the constant force, which is the tension, and then if you apply the concept of the virtual displacement, that is very a small angular displacement is taking place because of this tension force. So what is happening that like with this x position of this x and y is, you know that this is my L sine theta, and this is my L cos theta, and this is my x-axis, and this is my y-axis. This y-axis is coming down, minus y. Okay, so now if I try to write this r position vector of this is going to be xi plus yj. Okay, because x is, you know, this is L sine theta with the I component, this is L sine theta with the I component, but this y component is this one. Okay, but it's like in the negative y direction, so this is this j is basically basically minus j in our case, so this is minus cos theta j. So if you define the virtual displacement for this r, so delta r by delta theta, because now r is related to theta, and this delta theta. Okay, so delta r by delta theta, you know, this is going to be L cos theta I. Okay, delta r by delta theta with respect to theta, and delta r by delta theta cos theta going to be minus sin theta, this is going to be sin theta. This is my delta r. Now here delta theta is the virtual change in the angle. Okay, so this is actually the virtual displacement of the angle. Okay, that can be related with the delta r also, because so no, let's not go into that, but delta theta is my virtual change in the angle, which is a small imagined rotation, and that is because of my by tension force. So if the work done by this constraint, which is my tension force, is T dot dr, so T is, we know that T is, we know already, that is if you remember, T is my sine theta, this is my I component, and this is my jth components, T sine theta and T cos theta. Okay, so here also this T is going to have a component in this direction and one component in this direction, so this is minus T sine theta and this is T cos theta, so this is minus T sine theta and T cos theta, and delta r we have calculated here is going to be L cos theta times delta theta. So if you open this, these two are equal and we are getting a 0. So the work done by the constant force for this virtual displacement, which is in terms of the theta, is going to be 0, which is the principle of the virtual work. So work done by the constant force is 0. The other force is due to gravity. So second force is the gravity. So if you remember, the two forces which are acting is, one is because of the gravity, the other is the constant force, which is the tension. So the work done because of the constant force is 0. The other force is gravity, and gravity is the conservative force. So because the conservative force is there, it is going to be the conservation of energy. So I can apply the concept of energy conservation, that the kinetic energy plus potential energy is going to be constant. So now try to apply that concept. So kinetic energy is going to be half mv square. V is, in this case, V is basically x dot square plus, or basically this is Vxi plus Vyj, and Vxi is x dot I plus this is going to be y dot j. Okay, so V square is going to be x dot square, and y dot, this is V square is going to be x dot times x dot, this is going to be x square. Okay, so this is x square and this is y dot square, and then this is the potential energy. So because mgl cos theta, why mgl cos theta? Potential energy earlier when this bob was here, okay, at this position, the total length was from here to here is L. The total length is L, and now a bob reaches to this position, so the height it gains is this much, this height. So this height is L cos theta. This is L minus. So what is this height? The total one is L, and then this height is L cos theta. So this height is L minus is L cos theta. This is L1 minus cos theta. So this height is change in the potential energy from 0 to when it goes 0 to this position. This is mgl1 minus cos theta. Okay, so that's why how you increase the energy when you, this is mgh is 0, and then if I height h is, then this becomes mgs. The same concept is there for the pendulum. So now this is the potential energy, this is my kinetic energy, this is my potential energy. If I solve this, if I differentiating it, what I'm getting is m, because of these two and this two, this will cancel out. So I have m x dot x double dot y dot y double dot, because I have d dt of x dot is basically 1. I have what I'm doing is this is with x dot is there because x dot square is twice x dot, and this is d dt of x dot. This is going to be twice x dot x double dot. So this is half, this 2 will cancel out with this 2, and this is mgl sine theta, because the two term mgl, L is a constant quantity when I'm differentiating it. So from this I'm going to have mgl minus mgl cos theta. So this is going to be 0. So I'm left with mgl cos theta. Cos theta becomes sine theta, it becomes this quantity becomes plus. Now we have x is equal to sine theta and minus cos theta, and we know x dot y dot x double dot y double dot we already have calculated. If you put all these into here, you get the same equation, that is theta double dot is d2 theta by dt square equal to minus d by L. For a small angle, this is going to be theta. So again what we have is d2 theta by dt square plus omega square theta equal to 0, where omega is under root g by L. Okay, the same equation you're getting, but the difference is like when you do this Newtonian mechanics, you have to look for all type of forces that are acting on this. Okay, and then you equate all those forces and you get this differential equation. Okay, but when you apply the concept of the virtual displacement, and you know that the virtual displacement is saying that the work done by the virtual displacement is 0, so then you automatically get rid of the concept of this, what the constant force are doing. Okay, so when you apply this as constant force, and the virtual force is going to be 0, so you only bother about what the actual forces are acting on the system, and then you apply the conservation related to this system, and you have the same equation of motion, which can gives you what is your expression for theta, which gives you the configuration of the system. So if the work done by the constant forces are 0, then it is easy to solve the problem, and we need not to deal with the different forces and the components of the forces that we do in Newtonian mechanics, first thing. And the second thing is the concept of the virtual displacement. It is basically a mathematical tool which is developed to ease the calculation of complicated system which are under certain constraint, which we don't want to be bothered. So the condition, but the condition does not apply, for instance, when the non-negligible, that means non-holonomic constant or friction forces are present there. So then that is not going to be taken care. So on and all, and this is all for I'm now stopping this as from the next on the next we will further continue from here, that is the concept of the principal work, and then there will, this is for a static equilibrium, then we will go for this dynamic equilibrium sort of thing, and we will discuss the Lagrangian part. Okay, so this is all for now. Thank you very much.